to quantifiers. So quantifiers. Okay. Essentially, we're now moving towards that complex statement. Okay. There is a soulmate for every person. Okay, and remember, there were two versions of this. Version A was there's one soulmate who's the soulmate for everyone, that busy soulmate. And version B, that every person has their own individual soulmate. Okay. Now, I want to emphasize that this is a complicated sentence. It's a complicated proposition. Okay. And that has to do with the existence of what we call quantifiers. So let me underline the quantifiers. Okay, so in this case, let me sort of, there is a. So it's a quantifier. It's telling you how much of something, we're talking about. And for every person. Again, it's telling you how much of something. So it's for all the people. Okay, let me show you some similar sentences. Okay. Kilam has some gray hair. Okay, so here's the quantifier, some. It's telling you about how many. Okay, quantifier. Quantifier quantifies. Okay. Any map is 4 colorable. That means that you can color the map so that you assign countries with colors, you assign colors to countries, and no 2 adjacent countries have the same color. So we say that any map is 4 colorable. Here's the quantifier. It's telling you how many of the maps are 4 colorable. Basically, it's saying all. Okay. So this is sometimes called the 4-color theorem. It was only recently proved when you talk about the context of the history of mathematics, recently proved. Okay. Every n, so every integer n that's greater than 2 is a sum of 2 primes. This is what's known as Goldbach's conjecture. Okay, so where's the quantifier here? So every, it's talking about how many numbers bigger than 2, and in this, it's a very large number. We're saying all of them. Okay. Someone broke this faucet. Okay, where's the quantifier? Someone. Okay, it's telling you about how many, one person. Okay. There is a creature with blue eyes and blonde hair. Okay. These are all perfectly valid English statements, and they are complicated because of this quantifier. Let's finally end up with one that will be easy for us to sort of get to grips with. All cars have 4 wheels. Okay. Boom. Where's the quantifier? All. Telling us something about how many. Quantifying. Okay. So we're going to come to grips with this guy, and eventually we're going to end up, figuring out what's going on with that guy. Okay, so quantifiers. Okay, so all cars have 4 wheels. What are we really saying? Okay, so let's define the set of all cars. So the set of cars, C. Remember our way of defining sets. So the set of cars, C, is a set. Okay, and I'll use C to represent, little c to represent a generic car, where little c is a car. Pretty trivial definition of the set of cars. It's just that I've defined a set, and to belong to this set, you must be a car. Okay. Now, in order to make this statement sort of mathematical, we're going to introduce the concept of a predicate. Don't worry, nothing complicated here that you haven't seen before, but you may not have seen it in this way. So you've all seen the concept of a function. So f of x equals x squared. What does this do? It says that, give me a value x as input, and I will output x squared. So we could say something like f of 2. So f of 2 is equal to 2 squared, which is 4. Okay. We've all seen the concept of a function. Well, a predicate is basically a function. Now, when you have a function, you have an input and an output. And functions are very convenient and familiar to us because the input and output are both values. But technically speaking, when we formally define functions, we say there's a domain and a range and so on and so forth. Okay? So a predicate is exactly that. Okay? It's a function. We call it a predicate, but it's a function. Okay? The input is a member of some set. Now, just like functions, a predicate can have more than one input. So a function can have more than one input. A function of x and y. So a predicate could take as input, two objects, a member from set 1 and a member from set 2. Okay? But for the moment, let's consider a simple function. The input is a member from some set. So for example, this set. Okay? The output, now this is where the predicate becomes kind of unfamiliar. Okay? The output is a statement. Okay. It's not a value, it's a statement. Okay. And if I'm being perfectly meticulous, here's an example. I'm going to define the predicate just like I defined f of x. I'm going to define the predicate p of c. And remember what c is? C is a generic representative of an object from the set of cars. So this tells you that this predicate takes as input a car, which I'm generically calling C, and the output is a statement. Car C has 4 wheels. So for example, I can compute f of 2, I can compute p of, of Malik's Ford Escort. So that's a perfectly valid input because it's the label of a car. It's a car. So the output would be car Malik's Ford Escort has 4 wheels. Okay. Now that's a very bizarre statement. It's a very bizarre sentence, but if you think about it, it's perfectly correct. The car labeled Malik's Ford Escort has 4 wheels. Now in English, we usually just say Malik's Ford Escort has 4 wheels. Okay? But when we formulate it in this fancy way with a function that takes an input and outputs a statement, we have to stick to the format for the output. And the output has this format. So that's the sentence, that's output. A bizarre sentence, but perfectly okay. Okay. Now, all cars have 4 wheels. Okay. One way to say that is, for every car C that's in the set big C, so for every car C that's in the set big C, okay, now we'll use colons to sort of abbreviate, it is the case that. Okay, it is the case that, and we're going to assert P of C. And in parentheses, you can think of this as saying P of C is true. So we're asserting P of C. For every car C in the set of cars, it is the case that car C has 4 wheels, because that's exactly what this sentence is. This is equivalent to this. Okay, so mathematical version. Not a big deal. So we've just taken this sentence and given a mathematical way of formulating it. That's what we have done. Well, we're going to get more fancy. Okay, we don't like to say for every car. Okay, so we have a symbol for that. For every, that's called the for all. So we just say for all C. So this upside down A is a shorthand for all. So, okay, so let me translate this now. For all cars C in C. So the for all came from here. Okay, this guy is there. Okay, it is the case that, okay, so it is the case that came from here. Car C has 4 wheels. Okay, and that's P of C. So you see, this is a very long-winded way of saying exactly that. So for all cars, it is the case that car C has 4 wheels. That's exactly that. Okay, and this is just a notation that captures this. So the for all symbol, you say, you know, what set are you talking about? So your variable belongs to what set, okay? And then you assert the claim you want to assert. So that's an example. All cars have 4 wheels. Another example. There exists, there is a creature with blonde hair and blue eyes. So let me define the set of creatures. A is the set little a where A is a creature. Okay, and I'll define a predicate, a function, just as I did before. So a predicate that takes as input A, okay, is returning the statement, you know, A has blonde hair and blue eyes. So that's the statement returned by P of A. And now what is this saying? Okay, this is saying there is, so there, sometimes we say there exists, so there exists is the same as there is. There exists a creature A in the set of all creatures for which or such that that creature A has blonde hair and blue eyes, so for which we're going to assert P of A. Okay. So here's a formal way of making exactly that claim. Okay. And we shorten this, there exists a creature, so a creature A to a backwards E. There exists an A in, so this is there exists, backwards E, there exists a creature A in the set of all creatures for which we are asserting that P of A is true. Here, look at this complex English sentence, the same English sentence written in math speak, okay, using predicates and quantifiers. And the for all and the there exists quantifiers are the most common ones that we will use in this course. Okay, let me just show you that, you know, there are sometimes multiple ways to say the same thing depending on how you define your predicates. Okay. So here, let me define the predicate Q of A, not to confuse with P. A has blonde hair. So I'm simplifying the predicate. A has blonde hair. And R of A is the statement A has blue eyes. Okay. Then observe that I can make a compound predicate. So Q of A and R of A, because this is a statement and this is a statement, so I can take the and of a statement. So this is exactly the statement, A has blonde hair and A has blue eyes, which is exactly, you know, has blonde hair and blue eyes. Okay. So I can now rewrite this as there exists a creature in the set of creatures for which or such that I assert Q of A and R of A to be true. So you can have compound predicates. No big deal. So, you know, we are free to define predicates however we want, just as we're free to define functions however we want. The only question is whether the predicate is useful and what is the set that is involved in, you know, invoking some statement about the predicate. Okay, this is a quantifier. Okay.